All right, thank you very much. Hi, everybody. My name is Sebastian Zarrilli. Thank you for allowing me to share my work with you today. I'm going to be talking about my favorite star, MWC166A, with near-infrared interferometry. So let's get started. Why is this not working?
Click what your mouse on.
Okay, and then this should work. Is it this one? Okay, cool. All right, so first of all, I'm going to be giving a very small overview about the star itself, detailing previous observations and ones that we've taken with VLTI and Chara, mainly VLTI. I'll be discussing our continuum modeling for the star and its surrounding environment, and then some spectral line modeling that we did of the K-band lines from gravity. Okay, so MWC166. This is a very bright B-type star with a K magnitude of about 6.1. We know it was in the original list of Herbig AE/B objects, but this doesn't necessarily mean is exactly a Herbig star, hence the question mark at the top. It's been found to be photometrically variable over a couple of different lengths of timescales, but it's roughly around some months. And most importantly, we don't really have any idea of how old this star is. We know it's found in the Canis Major OB association, and there are indications that supernovae may have formed, triggered star formation there in between 500,000 years ago and 3 million years ago, but beyond that, it's not really entirely established. Okay, so here's a little SED for it from about 15 years ago now, but it's not going to have changed very much in the time. And we can see that for such a young object, it actually has an almost negligible near-infrared excess. So that adds a bit to the confusion about this star. We know it has a wide companion, MWC166B, about half an arcsecond away. But the MWC166A itself is a single-line spectroscopic binary with a rough separation of about 2 milliarcseconds-ish. So yeah. So what did we do? So we took several snapshots, about 13 or 14, using multiple instruments. So we have some observations over quite a long period of time, 8 years with Pioneer. We have 4 observations with gravity, which were taken about 4 years ago, and 1 shot from Merc-X. And when you're trying to analyze a binary, every shot is important. So kept that one, which is good. And so we analyzed all of these using our in-house modeling pipeline, Rapido, and also the previously mentioned in this conference many times, PMWAD. I love PMWAD, everybody should use it. It's amazing. Okay, so we first modeled this source as purely just 2-point sources, trying to get an idea of the astrometry. And we were sort of surprised at how well this actually worked. I mean, without the near-infrared excess, obviously we're not going to have a huge amount of continuum emission that isn't constrained to the stars themselves. But still, yeah, we knew this wasn't the whole picture because we had the systematic overprediction of the visibility models from the pure point source models. So clearly we need some sort of extended flux. But when we tried to model that, effectively, we know it's about 5 to 10% at each epoch, but the geometry of this extended flux is effectively degenerate in every model that we've tried. So we just kept it as a background, say we don't know the geometry, that's fine. The astrometry is okay, regardless. So fine, good. Wow, that is not what it's supposed to look like. But anyway, these are our visibilities and spatial frequencies. I have no idea why it's only loaded half of the graphics for each of these. Anyway, the model is in red and the data is supposed to be in black, and it's not on there. But effectively, the models fit the data pretty much exactly with the background model. I really have no idea why it's like that. Anyway, you'll just have to take my word for it, I promise. It does fit. And from this, each one of these shots yielded us some astrometric positions, which we used to generate a very first orbit of MWC166A. We also combined this with some radial velocity measurements from previous observations of the system, especially Pogodin et al. 2006 did calculate a radial velocity orbit for this system, and they calculated around 6 months in period. However, we find, oh my God, it's gone as well. Okay, on the left-hand side, at least we have finally some data and model together. This is our astrometric points. Yeah, so all of our astrometric epochs are on here. And you can see the fit is very well. Again, you will have to take my word for it on the radial velocities, but they also fit extremely well, apart from that one point in the middle that doesn't fit at all. And so you can see that with this astrometry now that we include, we basically confirm that the period of this orbit is actually twice as big as what the radial velocity only orbit said. And that's entirely natural, you know, if it's twice the period, it's still going to follow the same curve. So that was our first result with this system, which is great. And so, yeah, here we are quantizing it. So a lot of the parameters actually quite similar, or at least the ones like, for example, the radial velocity specific parameters like K1 and V0. Sure, okay, fine, quite similar, which is nice. Period twice as long. We find the eccentricity of the orbit to be about 0.5 compared to 0.028. And also very importantly, we constrain the inclination of the orbit for the first time to a relatively precise level. And it gives us about 53, 54 degrees of inclination. All right, cool. From this, we can constrain dynamical masses of the two objects, assuming a distance measurements, as was mentioned earlier. Another wrinkle in the understanding of this system is that the distance is also not very well constrained to the object. So you can see, yeah, so Gaia gives us 130 parsecs. And if you plot it on the dynamical combined mass and distance plot that we have here, we can see that that would actually correspond to 0.1 solar masses. So clearly for a B-type star, that's not quite right. In fact, our orbital solution does constrain any sort of distance measurements to really sort of above 800 parsecs here. And in fact, in our further calculations, we've basically taken the photometric distance from Kalchev and Hilditch 2000 of about 990 plus minus 50 parsecs as our benchmark sort of distance value that gives reasonable answers. Okay, yeah, and once you have the combined masses and the orbital parameters, we can disentangle these into the individual masses of the two objects using this horrible equation. And we did that, and we obtain some first actual individual masses for the two objects in the system. And so we see the primary star is quite massive, 12 solar masses, with a secondary at 5 solar masses. Now, I must say the uncertainties on these are relatively large, larger than you would probably expect with such an orbit. That's almost entirely from the distance calculation uncertainties propagating through. So if we get better distance, we can constrain this even better. Okay. Oh no, it's gone again. Okay, please imagine some stellar tracks on this HR diagram, which I will try and recreate. So the primary stars are the circles, and the secondary stars are the triangles. And oh my God, of course, it's got this away as well. Okay, I'm very sorry about this. The blue ones are our first stage estimate, our low stage estimate of 500,000 years. And the red ones are our largest stage estimate of 1 million years. And the orange one is 3 million years, and the green one is 1 million year. They don't really change very much between themselves. So if you can see the secondary star, if you sort of follow the laser pointer, you can tell that on the youngest stage estimate, that is still quite clearly still contracting onto the main sequence. Whereas at all ages, the primary star is already on the main sequence. And this is to be expected from something that is so massive. Even at 500,000 years old, the primary is going to have evolved onto the main sequence. And so for each of these, we derive the stellar parameters from some parsec isochrones, and then compared them to the parameters that were calculated by Fairlam et al. In 2015, and that is represented by the black cross, at least that's showing on here, with the caveat that, thank you very much, Fairlam consider this as a single star instead of a binary system. So, of course, though, it's going to be dominated by the primary. Yeah, there it is. And these are the parameters that I did. Okay, right. Let me go beyond this because I actually want to talk about the line fitting that we've done, which I think is kind of interesting. So we see some extremely prominent emission lines in the K-band. We've got bracket gamma and neutral helium. So we all know bracket gamma is usually found in the pure gas disk. It's in lower mass Young systems, it's usually associated with accretion. In this particular case, I went about a year thinking it was accretion. Now I don't think that anymore. I think it's actually a decretion. And so we can see here, we've done some modeling with PMOD to the line. We fit simultaneously visibilities, closure phases, differential phases, and normalized flux across the line. And so we see here we have the primary star and the secondary star as we fixed their sizes to the radii that were predicted from our stellar parameters. And then we have the bracket gamma and the helium emission either side of the primary. So we are assuming, and that's okay, that's somehow not in there either. So that's a shame because this is like my favorite plot, but nothing's on there. The slides will be uploaded with the correct stuff later. This must be a Mac PC thing. But anyway, the important thing is that we see this emission around the primary, and it's really close to the primary. And this is consistent throughout the epochs, even as the stars move. And so we interpret this as a actual decretion disk rather than accretion happening in this star, partially based on the radius at which the bracket gamma and the helium emission is happening. We found this to be around 12 to 13 stellar radii, which is more than is usually accepted for magnetospheric accretion, but is well within other studies of classical B stars. And I will leave you with my conclusion slide, which will summarize what I've been speaking about today. Basically, we now have some masses for this star. We've definitively characterized it as main sequence instead of a young stellar object. We've also excluded the Gaia distance from DR2 at least, which I have seen is still being used for this star. Might cloud some conclusions from other papers. And, oh, okay, I see a question. All right, and I'll leave it at that because I think I'm overrunning. Thank you very much.
Okay, thank you very much.
You.
Do we have any questions? Yes, you've got a question from Relay Alsmere. So what are your thoughts that it might be an evolved B bracket E star instead of a young star?
Well, my thoughts are that it possibly is. Unfortunately, again, the HR diagram isn't there, but effectively, so these age ranges, this 10 million years is something that I just came up with as a sort of reasonable upper bound. And this is in fact the only age for which the primary star is just starting to evolve off the main sequence. So I definitely think it's much more likely that it's that instead of a very young star. Yeah, I hope that answers the question.
Okay, thank you. Any questions from the floor? I have a couple of questions. So what do you think about this? So essentially the system is a hierarchical triple, right? You've got this distant source at 0.6 seconds, I think you said, and then spectroscopic binary. So do you think potentially that this outer tertiary companion could have caused the tightening of the inner binary that we now see?
Yeah, I mean, it's definitely possible. The wide companion doesn't seem to actually be dynamically interacting with the inner binary at the distance that it's at. So not at the moment, but it's entirely possible. Like this is, like these ages were calculated from looking at the movement of O and B type stars in this region, and it seems like there is quite a few. So it's absolutely, I mean, I'd say it's almost certain that in its very young life that it was interacted with, if not by the wider star, then others in the surrounding area, certainly.
Right. Okay, great. I think we're at time, so let's thank Sebastian again.